Okay, so last time we finished up probability distributions, and today we want to do one of the more famous probability distributions, and that's called the binomial distribution. Okay? So for something to be considered a binomial distribution, we have some requirements. Okay? So it's based on what we would call a binomial experiment. And so for it to satisfy as a binomial experiment, we would have these 4 requirements. Okay? So let's go through each requirement. Requirement number 1, each trial can be reduced to 2 outcomes, success and failure. Each trial can be reduced to 2 outcomes. And we call those outcomes success and failure. The second thing, there must be a fixed number of trials. All right. The third thing is these trials are independent. Okay. So the outcomes do not affect each other. They're not influenced. And 4, the probability of success remains the same for each trial. Okay, so these are the 4 things that we're looking for. Now I'm going to do an example. So let's say, for example, I flip a coin 10 times, and I want to see the probability of getting exactly 3 heads. Okay? I'm going to flip a coin 10 times, and I want the probability of exactly 3 heads. So let's take a look at that. That is an example of a binomial experiment. So here we go. Example 1. Flip a coin 10 times. What's the probability of exactly 3 heads? Okay, so I need to define a few things. Anytime we're doing a binomial probability problem, you're always going to define some things, okay? And these variables are very important. So we want to know what is n, we want to know what is p, we want to know what is q, and we want to know what x is, okay? So if you're going to do a binomial problem, you have to be able to define each of these. Okay, so n is the total number of trials. How many times are you doing what you're doing?
10.
10, right. And let me define that. So you have it in your notes. Total number of trials. Okay? P is your individual probability of success on a single trial. Okay? In this case, what am I looking for? I'm trying to find 3 heads. So your success is getting a head. Okay? And that would mean that failure is the opposite of getting a head, which would be getting a tail. Okay? So P is your individual probability of success. And in this case, what is my probability of getting a head on a single flip?
1 out of 10.
1 out of 2, right? Or 0.5. Okay? But in your notes, write down what this stands for. This is the individual probability of success on a single underline trial. Okay? Q is your probability of failure. Now, if you know what your success is, then what is my definition for failure going to be? The complement. And how do I do the complement?
1 minus.
1 minus P. Great. Okay? So if P is success and Q is failure, then Q is always just going to be 1 minus P. So in this problem, Q is also 0.5. Okay? Then X, that's the number of successes that the problem's asking for. Okay? In this problem, how many successes are they asking for? 3. Okay? So every binomial problem that you guys set up, you're going to have to go through these steps to find these variables. Okay? And then you're going to plug these variables into a formula, which I'm about to give you, or you're going to use your calculator, or you're going to use a table. Okay? So there's 3 ways to get these answers. All right, let me write down this formula for you, so you have it.
Would you say X was a possibility?
Yeah, the number that you're trying to find. In this case, we're trying to find exactly 3x. X is exactly 3. Okay? Here's my formula. The probability of exactly X successes, okay, in a binomial probability, the probability of exactly X successes is, we'll write it P of X equals NCX times P raised to the X times Q to the N minus X. All right, that's your formula. The probability of exactly 3 successes is NCX times P to the X times Q to the N minus X. So we're doing combination, N things, choosing X at a time. All right, let's fill this in, and then let's go to our calculator so we can solve it. So I'm doing a combination. N is the total number of things that we did, right? So 10, C, what is X in this problem? 3. So you're going to go to combination 10, choose 3, times P is 0.5, raised to the 3, times Q is also 0.5, raised to the 10 minus 3, which would be 7. Okay, so go ahead and type that in your calculator. Go out to 4 decimal places and tell me what this probability is.
Where did the 7 come from?
Oh, C.
The 7 is there's 10 total trials minus exactly 3 successes.
Oh,
So 10 minus 3.
okay.
Okay, so remind yourselves where to find these things on your calculator. And choose 3 times 0.5 to the 3rd times 0.5 to the 7th. Did you guys get 0.1172?
Yeah.
0.1172 approximately? 0.1172. Okay? And that would be how I solve that. Please make sure you understand how to get N, P, Q, and X, and how to plug it in your calculator. Okay? Okay, let's do another problem. Let's say we're having 4 children. And we want the probability of exactly 2 girls. Okay? So in this situation, we're going to have 4 children. What's the probability of having exactly 2 girls? So really quickly, let's run through what is n, what is p, what is q, and what is x in this problem. So, what is n in this problem?
4.
4. Why?
Total.
It's a total thing that we're doing, right? We're having 4 children. Great. What's the probability of success on an individual trial? What is success here?
Boy or girl?
Yeah, and in this case, what are we looking for?
Oh, girl.
Girls. So what's the probability of having a girl?
50?
50%, right? So just like the last one, 0.5. If P is 0.5, what is Q?
0.5.
Also 0.5. And how many girls are we trying to have? Exactly 2. Okay, go to your formula, plug in these values, and tell me the probability of having exactly 2 girls.
4.
You should have 4C2, 0.5 to the second, times 0.5 to the second. And you should get 0.375. Okay? Everybody get 0.375? Okay, great. I want you to keep going with this one. What's the probability of having exactly 0 girls? What's the probability of having exactly 1 girl? What's the probability of having exactly 3 girls? We've already done 2. What's the probability of having all 4 girls? Okay? So go ahead and spend a few minutes, and I want you to calculate all of these probabilities. 0 girl, exactly 1 girl, exactly 2, exactly 3, exactly 4. Okay? Calculate those and tell me what you get. And I'll put my answers up too, and you guys check with mine.
Oh, it's different. Yeah. So, x. Oh, that's n minus x. So it's n. Okay. You want to do n minus x? Oh no, no, that one is just x. It's just x. Whatever x is 2.
So double check as you're going through the formulas that you're getting these values, okay? You're just using the same formula every time. So on this one it would be 4C0, 0.5 to the 0, 0.5 to the 4.
Probability equals 0. How can I 0 is 1?
Everything stays the same. The only thing you're trying to find, the only thing that changes is the x. All other things stay the same besides x. X the only that changes. So, so 0.5, 0.5,
Oh, okay.
Okay, once you get these,
Yeah, I forgot it.
what I'd like you to do is put them in a probability distribution table. Okay, so a reminder from last class, what did that look like?
X over
You have
the
x,
table, and then the
p of x, right?
P of x.
in this problem, what is x representing? The number of girls, right? So what is my lowest possible number of girls?
0,
0. What's the highest possible number of girls?
4,
4. So we're going to have 0, the probability of having 0 girls, 1, probability of having 1, 2, 3, and 4. And we have the probabilities right here, right? 0 is 0.0625. 1 is 0.25. 2 is the first thing that we did, 0.375. 3 is back to 0.25. And 4 is 0.0625. Okay? So notice, this is a probability distribution. The binomial distribution is a probability distribution. Here's all of the possible things that can happen. You could have 0 girls all the way up to 4 girls, and here's a probability associated with each, okay? What do we know about if I added this row here, what would that have to add up to?
1.
1, okay? It is a probability distribution. Okay, when you have the whole distribution in front of you, you can ask more sophisticated questions. In all of these problems, we ask, what's the probability of getting exactly 2 girls? What's the probability of getting exactly 1 girl, okay? But now I can ask questions like, number 1, what's the probability of, at most, 3 girls? Okay? What's the probability of having at most 3 girls? What does at most 3 mean?
3 and above.
At least 3 would be 3 and above. At most 3 would be 0, 1, 2, and 3, right? So to get this answer, if I have the table sitting in front of me, you add up the things that you're looking for. If you could have 0 girls, 1 girl, 2 girl, or 3 girls, you're just going to add these up, and that will give you the answer to this problem. Does that make sense? So to solve this, you're going to do the probability of 0 girls, plus the probability of 1, plus the probability of 2, plus the probability of 3. So I would add this, 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 and this, and that would give me the answer to this problem. Okay, so go ahead and do that.
You
And
said
let's-
this binomial distribution is the same as a probability distribution.
that it is a probability
So
distribution.
this binomial problem is the same as the probability distribution.
So any probability distribution has 2 things. It lists out every possibility and it has a probability associated. I'm sorry, it lists out every outcome and has a probability associated with every outcome, and those probabilities have to add up to 1.
Mm-hmm.
Binomial distribution is a probability distribution.
Oh, good.
Yes. Okay, so let's add these, 0.0625 plus 0.25 plus 0.375 and plus 0.25 again, and you should get 9375. Okay, any question that I ask, you can use this table to solve, right? What's the probability of at least 1 girl? At least 1 would be 1, 2, 3, and 4. Okay, so question 2. At least 1. You'd have 0.25 plus 0.375 plus 0.25 plus 0.062. That would be your answer for at least 1. Because at least 1 is 1 and more. Okay? So at most and at least come up a lot in these binomial probability questions. Also a couple of other keywords. Between. What's the probability of between 0 and 4? Okay? Now, mathematics is a little tricky sometimes. When we use the word between in mathematics, we literally mean between, okay? Sometimes in English, we don't mean that necessarily, okay? So when I say between 0 and 4 in a math class, that means literally between 0 and 4, which means 1, 2, and 3, okay? Does everybody see that? Which is different because, you know, sometimes if someone was like, oh, okay, pick a number between 0 and 4, you think, oh, I could choose 0 and 4, right? Not in math class, okay? So in this question, between 0 and 4 means 1 girl, 2 girl, or 3 girls. So you would be adding up these to solve that question. Okay? So that would help you solve pretty much any question that I ask if I have the whole table sitting in front of me. Okay? All right. What I want you guys to do is look in the back of your book where you have the binomial distribution tables. And in this particular book, it's on page 770. And what I want you to notice is they have a whole bunch of tables corresponding to the binomial distribution, okay? So in particular, in this problem, what was my n in this problem? How many girls were we having? 4 children. And what was my p? What's the probability of having a girl? 0.5, right? So notice in this table here, if you look on the far left column, these are your n's. So let's go down to n equals 4. Everybody see that? Then the second column is 0, 1, 2, 3, and 4. Those are all of your possibilities. Now, as you scroll across the top of this table, it has p. That's your individual probability of success, okay? So let's scroll over to p equals 0.5, and then let's look at that table and check it compared to our table. So in our book, when n is 4 and p is 0.5, it says 0.062, 0.25, 0.375, 0.250, and 0.062. It's exactly the same here, except that I went out 4 decimal places, and this particular chart only went out 3. Okay? Does everybody see that? So you have all of the answers sitting there waiting for you, and you can just look those up. All right? What are the limitations on this chart, though? There's 2 very important limitations. One limitation is start turning the pages, and how high does this chart go? What's the highest n you see? 20, right? What if on a test I say, hey, we're going to flip a coin 21 times, and then blah, 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 right? So that takes you off of this chart, right? This only goes up to 20. What's another limitation? Look at those probabilities p's. You have 0.05, 0.01, 0.2. What could I do that would not let you use this chart? Have a probability of success that's not on there, right? What if the probability of success was 0.52, okay? That's another limitation. So be aware of the 2 limitations that this chart has, okay? All right, and then there's one more thing that is super awesome about the binomial distribution, and that is this. From a couple of days ago, when we did the mean, variance, and standard deviation from a probability distribution, it was a lot of work. Why? What did we have to do? Does anybody remember? How did I find the mean, or the expected value? You had to go through each one and do x times p of x plus x times p of x plus x times p of x and add all those up, right? How did I do variance? I had to do x squared times p of x plus x squared times p of x plus x squared times p of x, add all of those up, and then subtract the mean squared. Okay, these were long formulas that we had to deal with. Well, the great news with the binomial distribution is it's really, really, really easy to get these answers. And in fact, the mean is just this formula, n times p. Okay? You don't have to do any adding and squaring at all. The variance is npq. N times p times q. And the standard deviation is the square root of n times p times q. Okay? And that's super awesome because we don't have to go through that long-handed method of finding them. Please have these handy in your notes because they're going to save you a ton of time when you have to do a problem like this. A die is rolled 120 times. Find the mean, variance, and standard deviation for the number of 6s that will be rolled. A die is rolled 120 times. Find the mean, variance, and standard deviation for the number of 6s that are rolled. Okay. Before I can do this problem, I need to check, is this a binomial distribution problem? If so, what is n? How many times am I rolling a die? 120 times. What is p? When I roll a single die one time, what's the probability of success? In this case, success is getting a 6.
1 out of 6.
1 out of 6. If p is 1 out of 6, what is q? 5 out of 6. Okay, is everybody with me? Can you use this information to finish this problem off?
Yeah.
What's the mean? N times p. 120 times 1 6. What's 120 times 1 6?
20.
20. If I roll a die 120 times, do I expect to get an average of approximately 26s? Does that make sense? Well, it should, right? Because if you roll a die 120 times, 1/6 of the time you should get a 6, right? And 1/6 of the time you should get a 1, and 1/6 of the time you should get a 2, so on and so forth. So it should make sense that we have an expected number of 6s to be approximately 20, because it's exactly 1 out of the 6 times, okay? So remember, the mean or expected value should make sense, okay? All right, and then variance, just do 120 times 1/6 times 5/6. And if you jump on your calculator, see what that comes out to. $16.66 repeated. And then anytime I have a variance, how do I get the standard deviation? Just take the square root of it, right? So square root of your last answer. And let's approximate that. Approximately 40825. Okay? So again, make use of this. It's just a formula for the mean variance and standard deviation from the binomial distribution. Okay? You don't have to go through the long method. All right, any questions? Okay, good.